Good morning. So this will be the first of 6 revision sessions, revision stroke problem sessions. And we'll have 3 during this week, during what would normally be the live online sessions. So this would be the lecture today, now, and the problems class at 9 o'clock tomorrow, and then the lecture also tomorrow. At whatever the usual time was there. So there were 3 lectures a week. So the third lecture was a recorded one that you looked at your own time. So if you send me through sufficient questions or requests to do bits of theory or something, then I'll record a 4th supplementary session to be viewed at the last half of the week. Okay? So we have 1 of these weeks of revision sessions now, and then there'll be another in week 12, which is after the break, right, when the term starts up again. Sorry, excuse me. And well, I don't have any particular plan for these revision sessions. I mean, there are 6 of them. I just thought roughly I would, since there are 6 chapters in the course, I would take topics from each of those chapters in turn. Of course, you're free to suggest questions that you want to look at from any chapter at any time. Right? It doesn't have to be reserved for those chapters. But failing that, I would perhaps pick out exam questions that centered on, say, one of those chapters. So today we'll look again at chapter 1, right, for example, and I would try and find something that was relevant from the old exam papers as to that particular chapter. So that's the very rough outline of, I thought, what would happen. Do make suggestions if there's something particular that you want to do. I mean, these sessions are for you, right? So they're for your benefit, and you should suggest whatever you think is most helpful for you. About the exam itself, then you'll see, well, you'll know, of course, that it's, these exams will be being done. You'll get the exam paper online, and so it's kind of an open book, quote unquote. So, of course, you have access to your notes and the lecture notes and anything else that you may care to look at during this exam. So the past exams, of course, are not like that. They're the traditional kind of in a closed room examination. So the exam papers are not exactly comparable to what you might expect in January. So if you look back at some of the old exam papers, you'll see, give a definition of this, give a proof of that. Right? Well, for obvious reasons, you're not going to get questions that are like exactly like that. Right? So what would have been perhaps a definition is now some slight variation on what that definition might be. Say something or prove something or show that something maybe holds, and what that'll mean is that you have to know what that definition is in order to apply that definition to whatever that question is. So there tend to be questions that will be close to giving a definition of this, or there'll be questions that ask you to perhaps make a proof that's close to a proof that's in the notes, rather than just copying out a proof that's in the notes. So on the website, course website, there is a sample question of this kind. If you look down at the bottom of the web page, and actually what it is an old exam question that's just been tweaked to be of this form. Right? So the first part, usually in a question, it's traditional, you put something easy at the beginning of the question, such as one of these definitions. So this has been tweaked at the beginning so that it's like this. I guess looking at the question last night, I thought, well, it sort of perhaps ended up slightly easier than a traditional question might be, but perhaps not. I'm not sure. So, I mean, there's not a lot much more that I can say about the exam than that. I do make the plea, please, I beg you, when you upload the snapshots of your exam, can you please make it one PDF file, right, rather than a PDF file for each page? If you've got any questions about the exam, now's a good time to pose them. There is a revision checklist, which I sent out in an email last night, which you'll have got, well, as an attachment to your to that email. So do look at that. Again, of course, it's on the course website. So the revision checklist is, it's really just a sort of aid memoir, right? It's not a prescription of everything that you have to know, and all this and nothing else is sufficient for the exam, right? The idea is that it's just kind of a focus, a way of so as it were, it's a collection of bullet points on which to focus. So, I mean, I went through the course text and I thought I picked out, what are the more salient or important points in each chapter or section, and that's what it's a list of. So that's the spirit in which you should take it. It lists also precisely the things to be omitted, right? At various points during the course, I've said, okay, we'll skip this, and we won't do this theorem, or we won't do this part, and so on. So it gives a list there of the things that we've skipped. So you'll want to pay attention to that, of course, as well. Okay. I see there are a couple of questions come through. So I will address these in a moment. But as I've said, if you've got any questions either about that revision checklist or about the exams, do send them up. So one question says, normal exams, we fold down the top left of the front cover. Oh, I see, to maintain anonymity. Oh, yes, you're probably entirely right. I should have known this, or I should check this out. Yes, of course, the exam should be marked anonymously. So your name won't be, I will not see your name. Right. Right, yes, I was thinking of it like homework. Yeah, so probably you're not supposed to put your name on the exam, all right? That is, so I misspoke entirely there. So, okay. Yeah, so whatever system that they've set up, I'm not sure what that is, then there must be some anonymized way that the exam gets to the marker myself, right, about that. So, okay, so I'll just back up on that and just say, okay, well, there's one plea that it's just a single PDF, right, rather than lots of separate PDF pages. So good question there. Are all the exercises examinable? If not, some proofs use exercises. Are these examinable? There are a lot of exercises in the course. I mean, you can see this is perhaps intended to be some kind of book at some point, right? So there are more exercises than we actually use or actually look at during the course. Some of the exercises are starred, and these are supposed to be harder, right? And these are typically ones that we don't look at, right? These are ones that will be perhaps too hard to set as a weekly homework. Certainly we use parts of those exercises during proofs. For example, when we work out the rules of cardinal arithmetic. we refer back to an earlier exercise that talks about bijections between certain sets of functions, particularly when we're looking at rules of cardinal exponentiation arithmetic. Right? So you could say the proof of the rules of cardinal exponential arithmetic depend upon that exercise, those bijections between sets of functions. Right? So in a sense, yes, that exercise is examinable in the sense that you could be asked to prove a rule of cardinal arithmetic, but you would either be told you can assume this part of the exercise and perhaps actually be told what the exercise was, right? Or you'll be asked explicitly to prove bijections between those sets of functions. So I think the route to proving something during one of the questions, if it involves an exercise, it will kind of explicitly tell you what you have to do from that exercise. So that's one specific kind of situation. The exercises, for example, there's a lot of exercise on ordinal arithmetic, right? And some of these are quite hard, right? And you would not be expected to, of course, to memorize or know, offhand what the statements of those exercises are going to be. Right? You might be asked, I mean, this is quite possible, you might be asked to prove one of the statements that actually was one of the exercises. In particular, one that you may have done during the homework sessions, right? That's entirely in order. So in that sense, those exercises then would be examinable. Relevant to this is a question is, would it be acceptable to quote exercises we've solved when solving exam problems? Yes. State the property that's there in the exercise, and you can say, by an exercise, we showed blah, right? And you're going to use blah as a step in the proof. Right? So if you've got a good coherent argument that's based upon an exercise, then yes, state that this was then an exercise. So if the point of me asking the question, is for you to actually do the work behind the exercise, then it'll say so. Is there a benefit of still of learning some of the longer proofs, such as the recursion theorems? This is a slightly hard question to answer. I mean, you may find if you look back at old exam papers, they'll say, give a proof of the recursion theorem on natural numbers. Right? So obviously this is not going to be a question because you just copy the proof out. Right? So on the other hand, knowing how that proof went, right? Knowing that the steps of the proof, right? This could be potentially, I would say it could be potentially useful. So you have to know how that proof went and what that proof constituted. Right? You don't have to learn it or memorize it, right? To the extent that you could just write it out, right? That's not going to be on the cards. But the stages and steps of the proof there, this could be useful. I mean, I think in general, it's just because it adds to one's understanding. I think the proofs are something like the recursion theorem. To understand a lot of the course is to understand the principles of induction and recursion. How well-foundedness is kind of at the basis of induction and how induction allows us to prove recursion theorems. That's kind of a theme that's recurred throughout the course. So I think to understand those proofs is to understand quite a bit of what the course is on about. I mean, I think something like Hessenberg's theorem. I mean, again, I'm not sure whether there's been a question on, give a proof of Hessenberg's theorem in the past. I slightly doubt it. But again, there are aspects of that proof that have been asked about, right? Or pieces from it, right? I mean, there's an exercise that relates to that. So I think knowing how the proofs go is, if you're on top of that, then you're on top of a large part of the course. Right, those are the questions that have come through. Are there any others at the moment? Okay, well, thank you for those. And again, if there's anything that occurs to you later, I mean, I can repeat some of this again tomorrow morning, if need be. Okay, so let's then, unless there's particular work you want me to do, then let's look in chapter 1 and see, kind of summarize what's there and look at some exam questions, or maybe I go straight to some exam questions for that. Okay, and do sort of let me know, right? If you think there's something more useful in a way of format for these revision sessions. Okay. I seem to have mislaid my own set of course notes. Okay, here we are. So at the beginning of the course, we were just talking about some basic axioms and the idea of sets vis-a-vis proper classes. And sometimes there have been questions on this, right? So, for example, in the first few pages, we talk about the axioms of pair sets or the axiom of subsets. And if you look at, well, I've got in front of me here also, first question from the 2019 paper, right? So the question started out, state the axiom of pair sets. Okay, so let's just remind ourselves, sometimes called axiom of pairing or axiom of pair sets. So given any two sets X and Y, there's the unordered pair set XY. Question then continued, you were supposed to give then the definition of an ordered pair, right? Well, of course, this serves to, let's just remind ourselves, this is the ordered pair. And then an ordered triple is, again, an ordered pair. But the first thing is the ordered pair of XY. And the second thing is the third thing. And this is the basis for ordered n-tuples. So if you look in the text, you'll see by induction, we define an ordered n tuple, assuming we've defined ordered n-1 tuples. Here's the ordered n-1 tuple, right? And we just pair it up with the last thing, xn. So in fact, all of these ordered tuples actually are all ordered pairs of a special form, right? Here. And the Cartesian product of n sets, A1 to AN, this was the collection of ordered n tuples with AI coming from AI down here. One of our most basic axioms, axiom of extensionality. So this is a criterion for when two sets are equal. A equals B if for any object X, any set X, X is a member of A if and only if X is a member of B. And the things to the left of the epsilon sign are always sets, but the things to the right can possibly be proper classes. So there's also an axiom of extensionality for classes. And it's exactly the same, except we allow A and B here to be classes. And we saw that there were proper classes. Well, more of that in a moment. Right? The axiom of subsets that says if you've got a well-defined property of sets, definite property of sets, then for any set Z, you look at the collection of things in Z which have the property, then this is a set. Okay. So again, from that same exam question. So this is exam 2019, question 1. I mentioned I gave 1A, right? So 1B started out, state the axiom of subsets. Well, we've just done that. So then continued, using the axiom of subsets, or otherwise. Derived from the Russell class and it tells you what the Russell class is, or reminds you again. It's a class of all sets that are not members of themselves. The fact that V the class of all sets is a proper class. So this kind of formulation, use this or otherwise, it's kind of a hint, really. I mean, it's just saying use this. Right? I mean, you don't have to use this. If you've got some other method, okay, please deploy it, right? But usually this is the standard way of doing it, or you can choose some other way in the otherwise, right? If you want it. Right? Okay, so the idea here then is, I mean, indeed, you can find this. You can find this argument precisely there in the notes. Right? So okay, so a solution could be something like run along these lines. We can show that R, sorry, is not a set. And most people then gave that argument. Right? I won't repeat that now to save time because that's there in the notes, right, directly. And I'll show V is a proper class. So again, that is there in the notes. But anyway, this is to kind of remind us how that argument goes during this revision session. If V were a set, so then we should have that R is the collection of Y in V, such that Y is not a member of Y. We should have that this is a set by the axiom of subsets, which you've just been asked to write down. Right? But this contradicts the argument that would have just been given here. Right? So V is a set, sorry, is not a set, right? It's a proper class itself. V can't be put here in the axiom of subsets. So V is a proper class. So this was 1B. So 1C says was in several parts. Why are there not two distinct sets? So they're different, but both with no members. So it's asking why are there not two empty sets, two different empty sets. So it's asking you to deploy the axiom of extensionality. Right? So your answer here would be by the axiom of extensionality, x1 equals x2, if and only if, for all y, if y is in x1, if and only if y is in x2. Sorry, this is part of your answer. This answer is not quite finished yet. So if you recall, there was a lot of discussion about the empty set in the first couple of lectures, and a lot of the time it's a little bit confusing because there are logical implications about the empty set that are often kind of vacuously true, because it talks about all members of a set. So here we're talking about all members of this purportedly empty set x1, and all members of this purportedly empty set x2. So of course, x1 and x2 don't have any members. That's their defining property in the question. Right? So an implication like this is always vacuously true. For any y, if it's in x1, then it's in x2. But this never happens because there isn't such a y. So the p implies q is always true. Right? If the antecedent p is false, the implication p implies q is true. So these are always true. And in particular, for our two sets, x1 and x2, this is true. Right? So they're the same. So the right-hand side here, and I don't mind if you just say RHS for right-hand side, here is vacuously true. So x1 must equal x2. Okay, any questions? Okay, one C2. If f is going from v to v as a function, and f on x is the collection of z's such there is some y such that y is in x and f of y equals z, explain why f on x is a set. So strictly speaking, this isn't something about chapter 1. Right? So, okay, it even reminds you what this notation is, that the range of f on a set x are all those z's such that I can find a y in x such that f of y is z. Right? And so this whole question, number one here, is really about axiomatics, about axioms. So this is the axiom of replacement. So the solution here would be to say, solution. You just quote the axiom of replacement. For any set X, f on X is a set. That's all you have to say, right? See, the question is wanting you to just give the reason as to why we as set theorists take this to be a set. And it's because we have this axiom here. The second part of this to continued. So somebody asks, doesn't the axiom of replacement follow from the axiom of subsets? Or is there something I'm missing? Okay, let's put this on hold for a moment. So does the axiom of subsets imply the axiom of replacement? Is the question. Well, the answer is no. We do need a separate axiom to say this. What is let's give a diagram. Axiom of subsets says I may have the collection of, so if Z is a set, I can look at the x's in Z that satisfy phi of X. So here would be Z. And what the axiom of subsets does is pick out those elements of Z which have property phi, and leaves aside those that don't. Picks out the elements of Z with phi and leaves the others aside. And it declares that those that have phi form a set. The axiom of replacement is saying something else. Here's a set Z. I've got a function f. It's saying I apply f to all of the things in Z. And I've got another collection of things which result. If I were to somehow, if I knew that all of these things were contained in a set, I could indeed apply the axiom of subsets. Right? I could say, I'll pick out the things in this set T, which are in the range of F. But I have to know that these are contained in a set in order to do that and apply the axiom of subsets. I could put the T here then, and I could say, I'll pick out the Y's in T such that Y comes from F of something in Z. And that would be a perfectly good way of applying the axiom of subsets to deduce that there is a set which is the range of F. But there is nothing here yet that says when I apply F to the elements of Z, I get all these things over here, but there's nothing that tells me that they sit inside a set. And that's what the axiom of replacement does for us. It says, yes, I apply a function f to a set Z, actually there's a set exactly of its range. So, so we don't know a priori that f on x is contained in a set T so that we can apply subsets. Right? And the axiom of replacement remedies this. And it just declares that f on x is a set. What does a priori mean? We don't know. So we don't know kind of from the beginning. We don't know from the basics, from the start, that this is going to be contained in a set. So we don't know from prior knowledge, right? From prior assumptions. Contrast with a posteriori. This is kind of like after the fact. We know from what's happened that something is true. Right? This is, we know something is true on the basis of prior knowledge. This is, we know something is true because of some facts that have happened or some situation has occurred. So there's contrast, a posteriori and a priori. Okay, so, well, that's a bit of Latin for us. We didn't finish 1c yet, right? So if this point is clear enough now, then let's go on and do that. So this is still 2019. 1c continued. Can there be a one-to-one function f from the ordinals to the power set of omega? Right. Give your reasons. Okay, so solution here. Well, the thing to think about here is, well, it's a one-to-one function. But what I've got here is a proper class. Right? This was by Burali 40. It showed that the ordinals were a proper class. What we've got here is the collection of sets of natural numbers. Right? Well, the axiom of the power set says, you know, if this is a set, its power class is a set. So if the function was one-to-one, we could invert f on its range and have a map from a set onto all of the ordinals. And that will contradict the axiom of replacement that we've just mentioned. So there's several things packed in there into this. So I think here, so I would say something like this. The answer here is no. And you have to give reasons, right? On, we know, is a proper class by the Burali-Forti lemma. So you're giving that fact that we know we have. We have, by the axiom of power, power sets, that P omega is a set, since omega is. As F is 1 to 1, right, then its inverse is 1 to 1. But then F to the minus 1 is onto this proper class. On the other hand, the domain of F to the minus 1 is a subset of P omega. So it takes a subset of P omega onto On. Right? So what did I mean by that? So not necessarily part of your answer, but I mean, well, it could be. You could say, let T be the collection of Y in P omega such that there is an alpha such that F of alpha equals Y. So what I've written down here is a definition of F on the ordinals here. So the ordinal is not a set, right? So I'm not applying the axiom of replacement at the moment, right? I'm picking out using the axiom of subsets the range of F. This is a well-defined property of the sets Y and the alpha, such that F of alpha equals Y. So this is a set. Then T is the range of F on On is a set. Okay, so it's a subset of P omega. So F to the minus 1, right, this is taking T onto the ordinals. Because this supposition is it's 1 to 1 from F into O. Now we apply the axiom of replacement. F to the minus 1 on T is supposed to be a set. But it contradicts Burali-Forti, which we just mentioned. This is a contradiction. Okay. So that would finish that. So there's a question, why does f being 1, 1 mean its inverse is also 1, 1? Here? Well, in general, here's a set x. Here's this function f. And it's going over to y here. So it's 1 to 1, so it's sending different things to different things. Right? Then all you have to do to undo, I mean, this is kind of first year foundations and proof. All you have to do to invert the function, of course, is I go for these different things back to the different things they came from. So we can define f to the minus 1 on some u and v here. So that's that a or b. And because only one thing gets sent to u, there's only one a that it comes from. So the function is well defined. In the inverse function, f to the minus 1 is well defined. As f is 1 to 1, there's a unique a in x, so that f of a equals u. So this truly is a properly defined function. So f to the minus 1 of u is properly defined. And that's why f to the minus 1 is 1 to 1 on the range of f. F to the minus 1 is 1 to 1. On the range of f on x. So no, well-defined and one-to-one don't mean the same thing. What it means is the definition that I've put down here is a good one, right? It's saying I've properly defined what f to the minus 1 of u is, because there's only one choice of a such that f of a equals u. It's not ambiguous. It's not that there are two things, a and b, that get sent to u, and therefore my definition is bad by saying pick out that a, which does this, because there could be two candidates. I want f to the minus 1 to be a function, so there should only be one thing that u gets sent to. So being properly defined or well defined in this context just means I've got a good definition. Okay, so again, the question is, of course, the range of f on x, this is contained in y. It needn't be all of y. So we need not have that the range of f on x equals y. Right? It could be a proper subset of y. Without other information, we're not saying f to the minus 1 takes y into x, right? I'm not saying this. What I'm saying is f to the minus 1 takes the range of f on x back into x. Right? That's what we're saying here. So f to the minus 1 is 1-to-1 on its range. So we can invert it. Perhaps that was the source of the difficulty there. Okay, well, I hope that's clear now then. Fine. Okay, then that's time's up. So I'll see you again then tomorrow.